afternoon. Thank you. I personally thank organizer Amrita and Amrita Agarwal for this opportunity to share our recent venture in nano-aerated water agriculture. First of all, this is an exchange with the collaborators. Okay, so I want all of you to stay awake during the next 20 minutes. I know it is around 1.5 hours after the lunch, and it is a very difficult time to keep people awake. Just before going into the nano-aeration part, since we are here to develop proposals together, it is very interesting and very important to know our organization and our background so that we can talk with each other and develop different proposals. Many of you are not familiar with ICRISAT, so I will first mention what is ICRISAT. ICRISAT is an international research organization engaged in dryland agriculture. In India, we were established as an agreement with the government of India in 1972, and we are recognized as a United Nations organization operating over 50 years. We have several country offices in India as well as in Sub-Saharan Africa, where we are basically trying to help the low marginal farmers in the dryland agriculture. So, around 2/3 of the population today globally is suffering from water scarcity. We are all here talking about irrigation because many farmers we see today are having water scarcity issue. So this is the issue. Somebody told the core issue should be addressed so that the solution should be irreversible, right? That is a very good point you made. About 500 million people are suffering, and you can see the spread. It is spread across the world. So I'll give you the coming decade. This is the scenario coming. By 2050, we will have a population of 9 billion. Okay. For this 9 billion population, we need 60% more food because of the changing food habit. And for this 60% more food, we need 19% more water. How much water agriculture today consumes? It consumes around 70% of the water. So if we need 19% more water, you can understand the stress of the existing systems. And this is the per capita water availability in India. You can see the present figure. This is as per 2023 data. India has officially become a water scarce country with an average water availability of less than 1700 meter cube per annum per capita. Also the land. Somebody mentioned about agricultural land. Do you know how much agricultural land is there in India today? It was 144 million hectare when we got independence. Now it is around 139 million hectare. And it is not increasing. What is increasing is our population. So the per capita water availability as well as land availability is decreasing. So you can see the situation. So we have 17% of global population today and 4% water. Okay. So we are having big challenges. Why I am telling these figures? Because these are big challenges. When we started our career, we thought water scarcity will come someday in our life, but it has already come. And we are suffering, we are seeing what is happening in Bangalore. Agriculture is the main source of income. Around 65% of Indians live based on the agriculture. But they contribute only 17% of the GDP. So there is a problem. Water is a problem, land availability is a problem. Going forward, that is a problem. Do we treat our wastewater? That is another thing. You can see this is a Niti Aayog data about water treatment that we are doing. Mostly Eastern India, the water treatment is not that efficient compared to others. I will give you a global scenario. How about the globe? All countries, how they treat wastewater. High income countries, they treat about 70% of the wastewater they generate. But the situation is not so in the lower income countries and medium income countries. This is the total water as a humankind today we withdraw, 4,000 kilometer cube, and 70% of it is used for agriculture. Globally, around 36 million hectare is irrigated with wastewater. So all farmers even today don't have access to clean water. Many people here are talking about future technologies. When you design the technology, you assume the farmers are having access to clean water. But this is the size. 36 million hectare is close to the size of Germany. So that big area is without any freshwater irrigation. What are the main countries? Top 5 countries in this is China, India, Pakistan, Mexico and Iran. That's why we are here today discussing this topic. Totally around 885 million, this is a WHO report. This many people are affected. If you irrigate a crop with wastewater, consumer, farmer, vendor, everybody gets exposed to the health risk. How is the treatment scenario? How we are treating wastewater? We hear a lot in newspaper, in WhatsApp, what is the wastewater treatment scenario in India? See, we generate around 72,000 mld wastewater, okay? It is 2023 data. And we can treat only 28%. You can see 28% is fail, right, in exam. So if we treat only 28%, approximately we can say we don't treat our wastewater, okay, rather than, taking this other route. And the treatment scores they have released, this is a 2023 data released by Niti Aayog. They have ranked states in terms of their wastewater treatment efficiency. You can see eastern states, the efficiency is low. And this is our rural population, 90 crore. 90 crore people live in rural India. And they don't have access to any wastewater treatment. Have you seen any wastewater treatment plant in a village in India? It is not there. So in urban, we treat only 28%. And in rural, we just forget about it, that they don't need wastewater treatment. And this is the distribution as per the state. The blue bar here indicates the volume of wastewater. So bigger states like Uttar Pradesh, they exit more water. But the per capita picture is different. Some of the smaller states, per capita wastewater generation is more. And this is the spread of technologies. Why I am showing this? Because I am talking about nanotechnology or some new technology. So ideally you need to know the status of other technologies or whatever is existing. These technologies you will come across, all across. The ASP, if you have little land. If you don't have land, you can go for SBR. This together is the 28% we saw earlier. These technologies cannot go to villages. Why? Because these technologies are energy intensive. In India now, thanks to many developments, villages have seen electricity. But it is not very high voltage, 3 phases. Many equipments cannot be run in rural India. Chemical intensive. Skill intensive. If you make a very sophisticated wastewater treatment plants in a remote area, you may not get engineers to operate it. And inadequate design treatment capacity. These are the reason why after 75 years of independence, we don't have any wastewater treatment unit in villages. Wastewater reuse in agriculture, there is a lot of focus as per FAO. But one thing is there. Wastewater reuse in agriculture is there in countries like Israel, in Australia, in places like California. But here, Indian scenario, it is different. The treated wastewater in Israel gets auctioned, okay? But in India, you need to treat the wastewater, but the farmer is not going to pay for it, okay? So it should be free or very close to being a free. This cycle, I just want to know, this is the cycle we are experiencing, okay? We all say climate change, and climate change is making conventional agriculture unviable. So we see a lot of migration from rural to urban, okay? This migration of the population, where they stay, they don't stay in posh areas. They settle in peri-urban areas, okay? And this peri-urban area, what they get? They get the surplus urban sewage. If you go to any big city of India, the peri-urban area, you will see this peri-urban settlement people using this surplus sewage for vegetable cultivation. As per our one report published in 2014, most of the vegetables you eat in major Indian cities are grown on wastewater. Okay. And if you use wastewater, direct use wastewater in agriculture, it poses a health risk as well as soil degradation. because wastewater contains a lot of particles. It clogs the soil, and this cycle continues. This picture here is a farmer growing corianders using village rainwater, and they sell it to the next city market. Okay, that is how close. If they are using salad crop, cucumber, onion, tomato, which you eat or consume without much cooking, the health risk you can imagine. The sustainable development goal I saw, it is written in the entrance. This is the goal we are talking, 6.3. We are targeting by 2030, we need to improve the water quality by reducing pollution, eliminating dumping, and minimizing release of hazardous chemicals. This is our goal. And globally what we have seen, if you have invest $1 for wastewater treatment, the return is $5.5. So the economics is there. It makes sense to invest in wastewater treatment. Globally, this much area, 368 million hectare of area today, is actually irrigated. And globally, this is the total wastewater generated by municipalities, 317 kilometer cube. If you can convert this municipal wastewater safely for agriculture, it can irrigate 40 million hectare area. So going forward, we are saying that we need more water, we need to produce more food. So we need to do the recycling of wastewater, there is no other way. We had a project with European Union, it's a 9 million euro project, where we had several European and several Indian partners, because government was looking for a technology which can be applied in rural India, without chemical, without electricity. These are our 20 European partners, and these were our Indian partners. So together we were trying to develop a technology. This is the technology we designed. It is a phytoremediation technology which passes the rural wastewater through a gravel and sand bed, and this side we get a treated wastewater. The rural wastewater is a very dilute wastewater. It does not contain heavy metal. It is not a very strong COD or biological load wastewater. It can be easily brought back to agriculture safely. We have done extensive work on this with different plant species, how much is the uptake, what is the hydrology, what should be the size of each medium layer. These layers are different aggregates and sand, and I will just explain. These plants, they take up the nutrient from this sand. They are not growing on soil. So they will take up NPK, nitrogen, phosphorus and potassium from the wastewater. But plants don't take carbon. Okay. So the carbon gets degraded in the root zone by the microorganisms. Over a period of time, you will see the plant uptake is only 15% of the wastewater treatment. 85% treatment is done by this biofilm that is there in the root zone. We have this facility at ICRISAT Hyderabad campus where we tried different plant species, and we have a treated water pond. Here we are treating 36 meter cube water per day. This is a treated water pond, and we are using it for agriculture, because before doing this kind of work in farmer's field, you need to have in-house data, because in India, last thing you want to do in experimenting on farmer's field. Our farmers are very fragile. They can take extreme decisions if they face financial risk. This is the total facility. I'll just go through this, how we implement a wastewater treatment plant in a village. We typically involve rural community to make them involved in the project. Okay. Otherwise, if I go from Hyderabad and implement something, it will be my technology. It is very important to engage the local community, explain why it is important, and we can implement. So basically, this was the situation when we started the project. At the end of the rural drain, you will have this kind of a sump, and we converting it to a flower bed. This water they are using for certain crops which is safe for that purpose. We don't advise them to grow salad crops. Okay. Several units we have introduced as Uttar Pradesh, in Telangana, in other geographies. One unit we have introduced in Pondicherry with MSSRF as a partner. Across India, we have implemented several units, and we were asked to present to the PMO office one pager of our work, because they were looking for one technology which can work from Kanyakumari to Arunachal Pradesh without any customer care. This technology the villagers can implement by themselves without requiring any chemical or engineering support. These are various dissemination exercises we do about our work from the visitors as well as in different forums. These are some of the visitors to our site. Here it is a CEO of a company called Budweiser beer manufacturer. They produce a lot of wastewater and they are looking for ways to reduce their water footprint for sugarcane. This was a previous agriculture minister of Karnataka, Krishna Bairegowda. He was very interested in recycling of water for the Bangalore city, the problem that we are facing today. And we presented our work to the central ministry. Now coming to nano water, I'll just give you this because nano water agriculture, I don't think most of you have not heard. This is first time. So just these two slides, I will explain what is nano water. Nano bubble is an extremely fine bubble. The size is 200 nanometer or small. This behaves differently than any other air bubble. Normal air bubble will come up to the surface in few minutes. But nano bubble stays in the water like salt particle. Not for few hours. They can stay in water for months, weeks. So that makes a difference. You have a very oxygen rich water. The dissolved oxygen level in a water generally is varying between 5 to 8. But this water DO level will be 30, 35. It is very oxygen rich water. And this is the nozzle through which they pass a water and air mixture to produce the nano air. In India, and thus if you make one air bubble into very small size, the surface area increases. So the aeration efficiency increases multifold. That is why this technology is important. How it is affecting the agriculture? First of all, it breaks down the fertilizer molecules, makes it more available. It increases microbial activity. It stimulates plant growth. Together we see that a 15% yield increase already reported for paddy, soil microbial activity increase, and if it is a paddy fish dual system like Philippines, then we can see a optimal increase without any addition of chemical or electricity, because this is solar power system. This is a study recently coming from China, Academy of Science. You can see the root length is increasing when you are irrigating with a high oxygen water. And they have identified the genes which are responsible for this. This is for paddy. And for soil, we are seeing it can reduce the GHG emission from the paddy fields. Methane emission is a concern. Increase chemical fertilizer utilization efficiency and soil pH. We have published few papers, and if you want to follow our group, you can see the website. Whatever I presented here is a work of a team. As you can see, this is a multidisciplinary team, so I am only part of it. Thank you.
Long live India and France friendship.